Okay, so in our last video we talked about the rules for formalizing probabilities and our equation for conjoining probabilities. What's the probability of getting of two events occurring together simultaneously, like the probability of getting two heads in a row, or the probability of drawing two jacks in a row from a deck of cards. And what we saw is that both of these different ways of conjoining probabilities required two different kinds of equations. We had an easier equation, which was our restricted equation for probabilities that are independent of one another, that don't have memory of one another, that don't affect the outcomes as you go, like a coin flip. And we had a conjunction equation for probabilities that are dependent on one another, where the outcomes do have a kind of memory, where they're not exactly random, where they do have a structure based on one outcome, the next outcome is changed, which is like drawing two jacks in a row from a deck of cards. And for this, we had a general rule rather than a restricted one for determining our probabilities. Now, in this video, what we're going to be doing is very much the same, except instead of talking about the conjunction of events, we're going to talk about the disjunction of events. What is the probability of A or B happening, of X or Y, of outcome 1 or outcome 2? And we're going to see that there's going to be a very similar distinction between a restricted and a general rule, except this time, instead of the demarcation between our restricted and general rule being based upon the idea of independence, for disjunction, what we're worried about is mutual exclusion. So I'm sure this is a term all of you have heard before, something being mutually exclusive of something else. It's a technical term in inductive logic. So two events are mutually exclusive, the probabilities of which are mutually exclusive, when both events cannot simultaneously occur. So for instance, flipping heads on a coin is mutually exclusive of the coin landing tails. Likewise, the probability that it's raining right now is mutually exclusive of it not raining right now. That both events can't occur at the same time. A roulette wheel cannot give both black and red on a spin. And so in our everyday language, we use this term to mean something like the occurrences are disjoint, right? They're separate, that they can't both be true, as I just said, or that they're delimiting of one another, that the one event precludes the other event occurring. And so when events are mutually exclusive, and we're talking about the disjunction of probabilities, we get our restricted disjunction rule. Oops. Restricted disjunction. So restricted disjunction is used to compute the probability of two events that are mutually exclusive with one another. And the idea is to determine what the probability of each event or which event will occur. What's the probability of either of these events occurring? And our equation looks like this. The probability of A or B. And now notice, I could just do our deductive logic disjunction, the little mini v there, but I'll write or. The probability of A or B equals the probability of A plus the probability of B. And this is for when events are mutually exclusive. So what's the probability of, what example did I have? Yeah. What's the probability of rolling either a 1 or a 6 on a fair 6-sided die? Now, rolling a die, any one of the outcomes of a roll are going to be mutually exclusive of any other roll, because if you roll a 6, you can't also roll roll in a 3 on the same dice. To roll a 6 precludes all the other events, all the other possible occurrences, 1 through 5. Therefore, every roll of a die, every number of its face, is mutually exclusive of every other number of their own faces. So when we ask, what's the probability of rolling either a 1 or a 6? Well, the probability of rolling a 1 or rolling a 6. So what I've done is subscripted R1 is rolling a 1 and 6R6 is rolling a 6 equals, what's the probability of rolling a 1 on a dice? Well, it's 1 out of 6, right? Plus, what's the probability of rolling a 6? 1 out of 6. And this equals 2/6, which equals 1/3, which equals 0.33. So our probability of rolling a 1 or a 6 is 1/3, right? Because 2 out of the 6 possible occurrences of rolling the dice add up to 1/3 of the die's faces. So a couple warnings. If you're doing the rule of disjunction and you start adding up your probabilities, right, A, B, C, D, E, F, whatever, and you go over the probability of 1, then something has gone terribly wrong. Because recall, probabilities can only go up to 1. All probabilities occur between 0 and 1. If you have a probability less than 0 or a probability more than 1, then, again, something has gone wrong. But that shouldn't be a problem, and it might even indicate to you, if your probabilities do go over 1, that you need to be using not the restricted conjunction or disjunction rule, but the general disjunction rule. So here's a case in which well, okay, so let's do another example of this. What's the probability of drawing either a jack or a queen from a deck of cards? So the probability of drawing a jack or drawing a queen, again, equals, there's 4 jacks in 52 cards, plus there's 4 queens in 52 cards. And so what we see is that the probability equals the addition of both of those, which is 8 over 52, right? So that's, again, our restricted disjunction rule, where drawing a jack or a queen are mutually exclusive. You could draw either one of those. But what if I asked you, what's the probability of drawing either a queen or a club? So it's going to turn out this question, drawing a queen or a club, they're not mutually exclusive. And the reason that they're not mutually exclusive is because there's a queen of clubs. And we'll see why this is a problem that's going to require a general disjunction rule. If we were to just calculate this with our restricted disjunction rule, we would get the following probability. So what's the probability of drawing a queen or a club, right? So there's 4 queens in the deck, and there's 13 clubs. If we use our restricted disjunction rule, our answer is 17 over 52, and this is wrong. And as we work our way through the general disjunction rule, we'll find out why 17 over 52 is wrong, and why we need the general disjunction rule. So first, the formula itself, which is probability of A or B equals probability of A plus probability of B minus the probability of A and B. So what this is meant to do is to negate the problem that our restricted disjunction rule can't deal with, which is the problem of non-mutual exclusion, or mutual inclusion, as we might say. Okay, so let's ask the same question. What's the probability of drawing either a queen or a club using our general rule of disjunction? Well, the probability of drawing a queen, as we said, was 4 over 52. And the probability of drawing a club is 13 over 52. And then we're going to subtract the probability of 4 over 52 times 13 over 52. Right? Because the probability of A times the probability of B. If we recall from our conjunction, the probability of A and B is just the probability of A times the probability of B, and that's what I've written here, is 4 over 52 being the probability of A, and 13 over 52 being the probability of B, and we've multiplied them together. So this half of the equation equals 17 over 52, and that will be subtracted by, did I write it down? Yeah, minus, so when we multiply these two together, we get 52 over 2704, which, as it turns out, is equal to, if we reduce this fraction, 1 over 52. So we divide each half right by 52. Turns out that 2704 divided by 52 is 52, and 52 divided by 52 is 1. So we get 1 over 52. And our answer then is 16 over 52. So why did these give us different answers? We've plugged in the same numbers. Our equation here for our general disjunction rule, and recall that the general rule can be applied to any case even if it is mutually exclusive. So it's always going to give you the right answer no matter what. The restricted rule only works for mutually exclusive in the case of disjunction, or independence in the case of conjunction. And our restricted rule gave us 17 over 52. And yet the rule that works for any case gives us 16 over 52. So we should begin to be able to see why these answers, why the restricted rule doesn't work and why our general rule does. This is because we took the original probabilities of queens and clubs to be 4 over 52 and 13 over 52, right? For drawing queens and drawing clubs. However, these aren't mutually exclusive events. One of the cards shares queenness and clubness, which is the queen of clubs. And so what we should do is say, well, there's really only 3 queens that aren't clubs, and there's 12 clubs that aren't queens, and there's 1 queen that's also a club. There's 1 card that shares both properties of queenness and clubness. And if we add these together, 3 and 12 and 1, we get 16 over 52. So we recognize that mutual exclusion is important for the calculation of probability, because without it, we overjudge, or in some cases underjudge, the probabilities of certain occurrences. And this can often lead us to getting probabilities that are over 1 or that are just generally incorrect. And so when events are not mutually exclusive, we ought to use the general disjunction rule. Again, this is supposed to be an exemplification of why the general disjunction rule operates correctly in cases of mutual exclusion. So let's do one more example. Okay, so what's the probability of getting heads on either of two tosses? These events on two tosses, again, we're going to need the general disjunction rule, and here's why. If I say, what's the probability of A or B? What's the probability of getting heads once? Well, it's 1/2. Whoops. But what's the probability of getting heads a second time? 1/2. If we add these together, we get 1. Which means that it's certain that it happens. A probability of 1 is a necessary event. It must occur. It will happen. And how many times have you flipped a coin and twice and gotten heads both times? Well, surely you've flipped coins before, and surely you've flipped coins twice and gotten a tails, right? So our certainty should clue us off to the fact that something is a little wonky here. Something is not quite right. So for question, what's the probability of getting heads on either of two tosses? It is not going to be 1. You might get tails both times, right? And so we're going to need to recalculate this equation. So the probability of heads on flip 1 or heads on flip 2 equals the probability of getting heads on flip 1, which is 1/2, plus the probability of getting heads on flip 2, which is also 1/2, because every time you flip a coin, remember these are independent occurrences, but they're not mutually exclusive when asked in this way, is again going to be 1/2. But we're going to subtract the probability of 1/2 times 1/2, right? Because the probability of A times the probability of B, right? So what we get is 1, because 1/2 plus 1/2 equals 1, minus 1/2 times 1/2, which is 1/4, which equals so the probability of getting a heads on either of two flips of a coin is 0.75. It's not 1, because there's one occurrence where you get tails both times. And again, we can use a truth table to show this. So we have coin 1 and we have coin 2, or maybe I should say flip 1 and flip 2. So on our first flip, we'll say we get heads, heads, tails, tails. And our second flip, we get heads, tails, heads, tails. So on 3 of these lines, there's at least 1 heads, right? And our question is, what's the probability of getting a heads on either of two flips? Well, in 3 of those cases, we get a heads, but in 1 case, we don't, so it's not certain. But 3 out of 4 times, or 3/4, 0.75, we get a heads on either of our two flips. And this is how we calculate the disjunction of probabilities, and especially for mutually exclusive events. We don't end up with our answer of just 1. We get our correct answer of 3/4. And there you have it. That's our general rule of disjunction and our restricted rule of disjunction. We've also talked about mutual exclusion and the importance of distinguishing between these two rules. If you're working on a test and you recognize, or it's said in the question, that the events are mutually exclusive, then you can go ahead and use the restricted disjunction rule. But you can't ever go wrong with just using the general disjunction rule. And this is because even if the events are mutually exclusive, these will cancel each other out. But you don't have to worry about the back end of the math. It's sufficient just to know what these equations are and how to calculate them given the probabilities that we'll offer you in quizzes and tests going forward. Great.